Hello and welcome everyone to this another session of chromatography. I'm Sarita, Assistant Professor of Chemistry, Government Degree College for Women, Begumpet. So among all the other chromatography techniques, the most efficient one is HPLC. It is high performance liquid chromatography. So now today let us discuss about this HPLC, the principle behind it, the procedure, how it is being performed, how the separation is taking place, and also some of its applications. So HPLC, as that of other chromatography techniques, even this is also used to separate, identify and quantify each component in a mixture. It was formerly referred to as high pressure liquid chromatography. So high pressure liquid chromatography because in this technique we apply pressure for the separation. This is nothing but it is similar to that of column chromatography only, but where column chromatography, the separation takes place only because of the gravity. That is, the mobile phase will be traveling down because of the gravity. Whereas here in HPLC, we apply pressure to it. So that's why it is named as high pressure liquid chromatography. But now it is termed as high performance liquid chromatography, as its performance is very high when compared to all the other chromatography techniques. Now, what is the principle behind this HPLC? It is based on differential migration adsorption. So similar to that of column chromatography only, here the separation takes place because of the differential adsorption of the components to the stationary phase. So only the difference between the simple LC, that is liquid chromatography, and HPLC is, in HPLC, the technique is very speed, it is efficient, and it is sensitivity. And the ease of operation of HPLC is vastly superior. So we can easily operate this, and it will give very high results, very efficient results, and the resolution is also very high in the case of HPLC. Now, what is HPLC actually? What does it involve? Just a brief look at the technique. What we do here in HPLC is, here also we we take that is, we will be having two phases: stationary phase and the mobile phase. So here the stationary phase, it is packed with the tiny particles which are about 3 to 5 microns in diameter. Very less or small size particles we will be taking as the stationary phase. And the mobile phase is nothing but the solvents or the liquids we will be using as the mobile phase. Now, this mobile phase has to be injected into the column with the help of high pressure. So high pressure pump will be there where it produces some high pressure, and then the liquid, that is the mobile phase, will be pumped into the column. So when the liquid is being pumped into the column, and then after loading the sample also, the separation of the sample depends on the interactions which are present between the sample components and the stationary phase. So depending upon the that is affinity towards the stationary phase, the sample or the components present in the sample will get separate. And these separated components, after coming out from the column, they will be detected by a detector, and then it will be connected to a computer where we will get a that is chromatogram. A graph is obtained which is known as liquid chromatogram. So through that graph we can easily find out what is the nature of the sample as well as the amount of the sample which is present in the given compound. Now HPLC is nothing but a column chromatography, but high pressure is used in it. Now what are the mobile phases which are generally used in HPLC technique is water, methanol, acetonitrile. So all these are polar solvents which will be using in HPLC. And the stationary phases may be silica or alumina, which possess the polar sides and they interact with the polar molecules. Now suppose this is silica. As we know that silica is it is a polar in nature where we have OH groups which are bonded to the silica. And that is why it is acting as a polar site. Now, if we want to convert that polar site into a non-polar site, what we have to do is we have to just incorporate a hydrocarbon chain in it, a long chain hydrocarbon in this way. So here in the next example, you can see the same silica which was having OH group that has been replaced by a long chain carbon group. So it is known as octacylyl group. If it is 8 carbons, we call it as octacylyl group. If it is with 18 carbons, we call it as deca-octacylyl groups. So silica gel and chemically bonded octyl silyl groups and octadecyl silyl groups. So this chain completely is a non-polar. So if we want to convert a silica which is polar in nature to a non-polar, so what we have to do is just attach that OH group, that is the hydrogen, has to be replaced by octyl silyl groups or octadecyl silyl groups. So in this way we can convert the polar group to the non-polar group. Now these stationary phases, they should be, the particle size should be very small. If the particle size is small, then the surface area will be large. The columns generally we use in HPLC are 20 centimeters or less than that. The mobile phase, as I said, it has to be pumped into the column. So the pressure that can be applied is around 200 bars, or you can take it in SI units, that is 3000 SI or greater than this also. And the flow rate of the mobile phase is 1 to 3 milliliter per minute. So it is just 1 to 3 milliliter, that is, it is very, very slow. The flow rate of the mobile phase is very slow in the column. So as we increase the column length, so when we increase the column length, the number of theoretical plates per unit area will increase. So what it happens is, when the theoretical plates are increasing, that means we will get a high resolution spectra. And the resolving power increases when the column length increases. So when the column length increases, theoretical plates per unit increase, therefore the resolving power also increases. And if the particle size decrease, so when you take a very less diameter particles, then what happens is the surface area will increase. So thereby you will get high resolution spectra with HPLC. So these are the columns that we generally use in HPLC. They are made up of steel. You can see they are obtained in different various lengths, and these are used in HPLC. We will have a look at the instrumentation. So how the HPLC is being done. So this is the schematic diagram. So in this you can see that this is solvent which is acting as a mobile phase. Okay, so that it is being pumped. We have a pump here which is solvent delivery system, and before it enters, the solvent enters into the column, we have a sample injector here. So sample is being injected before the solvent is being entered into the column. So because of this high pressure, both the mobile phase and the sample will now enter into the HPLC column, where the separation will take place, and then the components which are being separated will be detected by the detector, and this detector is connected to a computer where you will get a chromatogram. And the waste material, that is the waste solvent, whatever is coming out, it is collected in a beaker. So in the instrumentation part, we have main 5 different parts under this. One is the pump, injector, column, detector, and computer. Now let us see in detail about all these different parts in HPLC. So first is the pump. This pump is mainly used to pump the mobile phase. So as the mobile phase is liquid only, we can easily pump the mobile phase into the column, and it is expressed in milliliters per minute. Generally, the normal flow rates in HPLC are 1 to 2 ml per minute. So just 1 to 2 ml per minute flow rate will be fixed with the help of the system. So in the system itself, computer system, you can just load the data. So according to that, the mobile phase will be it will be entering into the column. And the pump pressure, the pressure that we can apply is from 6,000 to 9,000 psi or 400 to 600 bars. So when the pump, this pump, what it is doing, it is helping in the passage of the mobile phase into the column. So here we have two methods. Either you can use the same mobile phase composition, that is the composition of mobile phase can be kept constant, which is known as isocratic, and or else you can increase the composition of the mobile phase, which is known as gradient method. So what is the difference between these two, we'll see. So pump modules are of two types. Isocratic pump. So what it does is it delivers constant mobile phase composition. Suppose if we are having two liquids, liquid A and B, two solvents. So A and B, if you want to, that is if the composition, if you want to maintain that as 1:1, so that will be maintained throughout the experiment. Or if you want to change the composition, suppose if it is 1:2, so that also it can be fixed and the same composition will be maintained. So in isocratic pump, whatever composition we need, either it is 1:1, 1:2, any ratio, so that composition will be maintained. So here the solvents must be pre-mixed. We have to mix that, everything will be given, that is it will be, data will be given in the computer, so that according to that it will be pumped into the column. And this, the cost of this pump is very low also. And gradient pump. Gradient pump is mainly, it delivers variable mobile phase composition. Suppose if after 5 minutes of running the column, if you want to change the mobile phase, okay, composition of the mobile phase, then you can change by using this gradient pumps. So it can be used to mix and deliver an isocratic mobile phase or a gradient mobile phase. So either you can go for isocratic or gradient mobile phase by using this gradient pump. So in this gradient pump, we have two types, binary gradient pump and quaternary gradient pump. Binary gradient pump, it delivers two solvents. So two solvents can be delivered at a time and by changing the composition of one of the solvent also. Whereas in quaternary gradient pump, 4 solvents can be used. And we can also change the composition of any particular solvent during the experiment. So isocratic pump is for maintaining the same mobile phase composition throughout the technique, whereas gradient pump is mainly used to change the mobile phase composition. Now you can see what is the main advantage of using gradient pump is, first we'll say isocratic. Isocratic is simple. So it remains constant with time. The composition is remaining constant with time. Even in the graph, you can see this is the red line, which is constant throughout the time after 5, 10, 15, 20, 25 minutes also after running Hplc. The concentration of the mobile phase is constant. And it is used in for simple separations. Oftenly it is used in quality control applications also. Whereas gradient, what we are doing is, the mobile phase, suppose if A and B are there, so the B composition is increasing with time. So even in the graph, you can see the blue line, blue colored line, it is the composition of B component is increasing with the time. So this change in composition of the mobile phase can be achieved by gradient method. So why this method is used is, it is mainly used for analysis of complex samples. If the sample is having more components, then we need to separate all the components. So by just changing the polarity of any one of the mobile phase, we can achieve the separation of the components. So it is used in method development for unknown mixtures, and linear gradients are most popular. So gradient method is where we are changing the composition of the mobile phase, whereas in isocratic, the composition of the mobile phase will be same or constant. Then now sample injector. The sample has to be injected into the column. So this we can do it by manual method or by auto injector also we have. So manual injector is where we will be injecting the sample here. Okay, it will be injected with the help of the syringe. Okay, first we have to take the sample in a syringe and then we have to inject it. Then you have to close it and then open the knob. So when you open the knob, that sample, whatever we have injected, it will enter into the column. So this is a manual injector. So if we need auto sampler method, in this case, what we have is, in the diagram, you can see these are the vials. So what we do is, if we are having more than 100, okay, about 100 samples are there, we cannot keep on injecting with the syringe one at a time. So what we have to do is, we have to take those samples and fill it in these vials. Okay, and then we have to fix the program in the computer. So which vial you want to use, that is which sample you want to use for the separation first. So like that, you just program it and leave it. So it will be automatically, the machine will take that particular vial, it will select that vial, and then it will, that is, it will take the volume also, how much sample volume you have to inject, that also we have to give in the program. It will take that much of the sample and then it will inject the sample into the injector, that is the column. So this is nothing but we use this when for automatic operation. When there is no person to do all this, we can go for auto sampler method. So all the samples are taken at a time and they are feeded into the computer. The computer programming has to be set, and then it will automatically take the sample and then it will inject into the column. So this is how the sample is being injected, either by injecting with a syringe or by using this automatic machine. Then column. So column is very important and it is considered as the heart of the chromatograph, because that is where the components are getting separated. Now these columns, what happens is, because the particle size is very small and we are applying pressure also, because we will be applying pressure, that is the mobile phase as well as the this one sample, it will be allowed to fall into the column by some pressure. So what happens is, at the starting of the column, it will show some resistance. Okay, because of the small size of the particles, it will show some resistance, because it will, as the fluid is coming at a time into the column, so after some time, then only the solution will be absorbed into the column and then the separation will go on smoothly. So this column has to be, as I said, it is having a, it is packed with the stationary phase, and the stationary phase we have seen, you can take silica or alumina which are polar, or else you can convert the polar into a non-polar groups also, and you can easily pack that into a column. So in this column mode, we have 4 different types. One is normal phase type, you can do HPLC by normal phase, reverse phase, size exclusion, and ion exchange. So normal phase, reverse phase, size exclusion, and ion exchange. So these are the 4 different modes by which you can proceed through HPLC. So what is the main difference between all these 4 is, first we will see the normal phase. So normal phase is very simple. That is, it is nothing but what we do is, we just keep the stationary phase as more polar and the mobile phase as less polar when compared with that of the samples. So this point you have to remember. See, in this normal phase, the packing must be more polar. So packing means what? Here the stationary phase. The stationary phase should be more polar than the mobile phase with respect to the sample. So just remember, in normal phase, stationary phase is more polar. And example we are giving that of the silica. Here you can see the OH groups which are exposed, which are bonded to the silica. So that is acting as a polar group. Now when this column is packed with such polar stationary phases, that is silica or alumina, now what happens to the components, how they will get separated? and which component will be first eluted out. So here the separation, you can see here we have different colors. These are different components which are coming out, dark blue, light blue, and the red. So which component is coming out first? It is the red component. So red colored one. So here the same, that is the principle is observed in all the techniques, where more polar the stationary phase, what it will do, it will absorb more polar groups. So more polar groups are absorbed more onto the stationary phase. And the components which are eluted out first will be less polar. Okay, because the mobile phase is less polar. So what it will do, it will have more affinity towards the less polar components, and then as the mobile phase is coming out of the column, it will bring out all these less polar components. That is, the less polar components will be eluted out first. So in this normal phase, the components elute in increasing order of polarity. So increasing order of polarity means less polar components are first eluted out, then comes least polar. So even here it is shown dark brown, dark blue is most polar, because it is, as it is more polar, it is having more affinity towards the stationary phase, and it will travel very slowly. So least polar, that is the red component, will travel faster, and that is eluted out first from the column. So this is about the normal phase. Then the second type is reverse phase. So reverse phase exactly reverse to that. Now in this case, the stationary phase is non-polar. Okay, and the mobile phase is polar. Now, so in this, what happens is, in the previous case, what we have seen, stationary phase is more polar, whereas here stationary phase is non-polar. So what we need to do, because when you are taking silica, in the previous case, you can see silica which is having OH groups. It was polar. Now what we need stationary phase which is non-polar. So what we have done is, so we have taken C18 carbon with silyl group, which is bonded to the oxygen. So when you, in place of hydrogen, that hydrogen is replaced by octadecyl silyl group, so that this long carbon chain will act as a non-polar group now. Okay, so this is taken as a non-polar group as a stationary phase, and then it is packed in the column. And now the mobile phase should be polar. So what are the polar mobile phases that we can take are, we can take some organic mixtures such as methanol water or acetonitrile water. These are some of the mixtures which act as mobile phases in reverse phase type. So now when the sample is loaded in this column, okay, now what happens, we'll see. So in this case, it is exactly reverse. So what are the components which are eluted out first? It is this one, dark blue colored components. So this dark blue colored components are less polar. Okay, they are less polar when compared to the red components. So components elute in decreasing order of polarity. So as the mobile phase is polar, so more polar components will be eluted out first. So more polar is a blue colored component. So those are eluted out first. Then comes the light blue, and then the red. Red is non-polar component. So that non-polar component is having more affinity towards the stationary phase. So that is why it will travel a bit slow when compared to the other components. So in this reverse phase, you have to remember that the stationary phase is non-polar and the mobile phase is polar. So the components which get eluted out first is the polar components here. The third type is size exclusion. So size exclusion is nothing but it is based on the molecular size. So size of the particles we deal with. Now here the column will be filled with the gel beads. Okay. So this column here, it will be filled with gel beads. And when we have the sample with the different sizes, small and the larger size particles, what happens is here all the small size particles will have affinity towards those gel. That means the gel will be having small pores where the small sized components will enter into that gel beads. Okay, whereas the larger particles, they cannot enter. So these larger molecules will get eluted out first. So after the larger particles get eluted out, then comes the smaller molecules will elute slowly. So in size exclusion, it is the larger particles which are eluted out first. And the last type is ion exchange. Now in the ion exchange chromatography, we have seen what is ion exchange. So here the separation takes place based on the charges which are present on the stationary phase and that is the resins and the sample. So here the same principle is applied here also. So charged groups of opposite charge to those charges on the stationary phase. So based on the charges that the exchange takes place between the stationary phase and the sample. So that is nothing but here in ion exchanges, we have two types of ion exchanges. Those are anion and cation exchanges. Now we'll see those two types. So first a cation exchanger. So as we know that in the last class we have done this ion exchange chromatography. So there also a cation exchanger is nothing but where the counter ion is cation. And that particular counter ion, that is the cation, will be exchanged with that of the cations which are present in the sample. So even in this case, you can see an example there, the silica, which is having Na+, that is sodium ion. Sodium ion is the counter ion. Okay, so that sodium ion will be exchanged with the ions, cations which are present in the sample. So in this, you can say the exchange of cations takes place. So positively charged species adhere to the support and the later eluted with acid. So all the positive species will stay there. Okay. All the negative species will get eluted out first. And then later on, by changing the buffer, strength of the buffer, the positive charged species also will be eluted out. So similarly, we have anion exchange. So in anion exchange, the silica will have the counter ion as anion. So here in the example, you can see this is the anion exchange where Cl minus fluoride ion is the counter ion. So this Cl minus will be exchanged with that of the anions which are present in the sample. Okay. So the negative charge species will adhere to the support and are later eluted with the acid. So first the positive charge species will eluted out first. Later on, all the negative charge species will be eluted. So these are the four different modes where we can use for this HPLC technique. So first one was normal phase. Second is reverse phase. Third is the size exclusion, and fourth is ion exchange. Now these are again the modes of high performance liquid chromatography. Now in this chart you can see what are the different types of compounds that can be used and what is the mode we have to in which mode the separation is taking place, what are the stationary phase and mobile phases used. So in the first type you can look, it is neutral, weak acid and weak bases, and the mode what we use is reversed phase. Stationary phase is C18, C8, C4, cyano, amino, everything. Mobile phase, water or organic modifiers can be used. Then for ionics, that is bases, acids, we generally use ion pair mode. Again, the stationary phase is C18, C8. Mobile phase is same, water or any organic, or it is ion pair reagent can be used as a mobile phase. Then compounds not soluble in water. So there will be some compounds which are not soluble in water. So for that, we can again go for normal phase, where the stationary phase is silica, amino, cyano, diol, and then mobile phases, some organic compounds can be used. Ionic, inorganic ions. So whenever we have inorganic ions, best method is ion exchange chromatography. So based on the sample that has to be separated, you can take either anion or cation exchange resin, and mobile phase will be buffer solutions. Then high molecular weight compound polymers. So whenever we have this high weight compound polymers, we can do this by size exclusion method. So why? Because in size exclusion, as we have seen that large size molecules will be eluted out first. And then in the stationary phase, that is used as polystyrene silica. In the mobile phases, gel filtration, aqueous, or gel permeation, which is organic based. So these are different modes of HPLC. Then, so after all the components, after the separation of the components in the column, now the end of the column will be connected to a detector. So all the components will be detected there, and the various detectors that we can use here are UV visible, mass spectrometers, refractive index, fluorescence, light scattering method, electrochemical, radioactivity, conductivity. So any of these detectors can be used. Then this detector has to be connected to a computer. So as I said, everything will be done with the help of computer, where the programming will be done on that system only. So all the separation and the collection of the waste, that is the mobile phase, which is coming out from the column, will also be collected in separate containers here. The computer not only controls all the modules of HPLC instrument, but it takes a signal from the detector and uses it to determine the time of elution of the sample components. So as I said, a chromatogram we will get. So that chromatogram will give information about the qualitative analysis. That is, what is the type of the component that has been eluted out. That means based on the time of elution, we call it as retention time. So retention time is nothing but the elution time, how much time the component has taken to travel the column. And also we can, with the help of that chromatogram, we can also determine the amount of the sample which is present in it. Okay, that is nothing but we call it as quantitative analysis. So that we can easily, that is also computerized. Everything, the feedback we will get from the computer itself. So this is how the chromatogram looks like. So in this case, we have two peaks, so which indicates that there are two components present. On the x-axis, you can see it's a retention time there. And on the y-axis, it is intensity of the peak. So the area under this, the area under the peak will give the amount of the sample present in it. So this is another example of HPLC chromatogram of food additives. So food additives, we add all this caffeine. You can see here caffeine, aspartame, benzoic acid, sorbic acid are the additives which are added in the food. Okay, all these. So if you get a sample and what are the various food additives it contains, that also we can determine by HPLC. So by getting different peaks, that is the elution time, you can see the chart. So all this will be recorded in the computer itself. What is the retention time of caffeine, aspartame, like that, and what is the area covered under that peak, what is the height of the peak, and the amount. So finally, it will calculate the amount of the caffeine which is present in milligrams per liter. So this is how it is all automated. So that is why we say that HPLC is very efficient and it's high speed. So everything is that is programmed, and you will get a neat picture of the various components present in the sample. So this is about HPLC, the different, what is the principle and different instrument parts which are present in HPLC. So just we'll have a brief of this HPLC, what we have covered. So mobile phase, sample, stationary phase, silica, alumina or cellulose, and the mobile phase has to be added from the top. This is column chromatography, what I am showing now. So because of the gravity, the mobile phase will be flown. Now here in HPLC, we will be using high pressure pump. Okay, pressure up to 40 megapascals. So high pressure pump is used to pump the mobile phase. And the stationary phase, what we use is same thing, but it should have very small particle size. So when particle size is less, the large surface area it will have, wherein separation will take place very nicely, and you will get a high resolution of the components or the high resolution chromatogram. Now in the components, first component is column. So this column is made up of stainless steel, and it can withstand up to a pressure of 50 megapascals. So you can see the length of the column is 5 to 25 centimeters, but the diameter is 4.5 millimeters. So the various column lengths you will be having, the flow rate will be 1 to 3 ml per minute. So all this you have to remember, the size and the flow also. Then the column, so stationary phase, adsorbent material. So it is chemically modified. You can have silica, divinyl benzene, etc. So the stationary phase may be polar or non-polar. So depending upon the type of the sample what you want to separate, then you can change the stationary phase. Then the mobile phase. So mobile phase also, it can be polar or non-polar. So the selection, again, it depends on the type of the sample. So those solvent here we have to store in a solvent reservoir, okay, from where it will be pumped into the column. So by applying some pressure from the reservoir, solvent reservoir, it will be pumped into the column. So before it is entering into the column, we have to inject the sample also. So sample injector is also there. Now when the sample is injected, there also a little bit of pressure will be applied. So after the sample is injected into the column at the end, it will be connected to a detector. And that detector again connected to a computer. So detectors, as we have seen, that is UV, IR, refractive index detector, mass spectra, electrochemical detectors, various detectors are there. We can use all this. Then, so when the sample is injected into the column, separation will take place. So here you can see how the separation is being taking place. And as each one of the component is coming out, you will get a graph like that. Retention time on x-axis, and on y-axis it will be the intensity. So when we are taking a standard, suppose glucose here we have taken as a standard, and if we run the glucose Hplc, so we'll get a graph there at retention time 5 minutes. So this is a standard time for the glucose. Suppose if we take any other compound, suppose if it is sucrose, so the peak is observed at 8 minutes time. Now if we have any unknown sample, and if we run that sample, and if we are getting the peaks in this way, okay, so you can see at the 5 minutes, it is nothing but it is showing that of glucose. So you can say that glucose is present in the sample, whereas at 8 minutes, there is no peak which says that sucrose is absent. Okay, so glucose is present, sucrose is absent. And the unknown peaks which are formed, that you have to again check with any other standard compounds. So in this way, we will be finding out the, determine the various components present in a mixture. Suppose if you want to find the concentration of the sample now. So how we can do is, we have to again run the Hplc by taking different concentration of glucose, 10, 20, 30 millimolar. This same retention time will be there, but the area under the curve will differ. Okay, with increase in concentration, the area under the curve will increase. So you can see here, more concentration, more is the area. Now, if an unknown sample is there, and if we are getting such peak, so this is 5 minutes, that is glucose, and the area under this, we have to check with that of the any other peak. So that will give with the standard values of the glucose, you can find the area also. So as I said, Hplc types, 4 different types. First is normal phase Hplc, where the stationary phase is polar, mobile phase is non-polar. So when stationary phase is polar, so polar components will have more affinity, so they will travel slow. And the first computed, that is the first eluted components will be non-polar. Okay, non-polar molecules will move first, or they will be eluted out first, along with the mobile phase. The next one is the reverse phase. So just reversing the stationary and mobile phase. Stationary phase here will be non-polar, mobile phase will be polar. So non-polar will stick to the stationary phase, affinity will be more, so polar molecules will move down the column along with the mobile phase. Okay. Then size exclusion, it is based on the size of the particles. So these are the porous beads. So small particles will enter into these pores. So therefore large size particles will come out first, or large size particles will be eluted out. So red one is, you can see small molecules entering into the pores, whereas the large size molecules, the green colored one, will be eluted out. Then HPLC with the ion exchange. So as I said, it is exchange of the ions. So either we can go for positive exchanger or a negative, that is anion exchanger. So based on the cation exchanger and the anion exchanges, the components will be eluted out first. So it is separation occurs based on electric charge. So this is how HPLC will work and how we can determine the unknown components present in the HPLC. Now let us look at the applications. So applications, as I said, very useful applications are there even for HPLC. It is used for separation of chemical and biological compounds that are non-volatile. Okay, generally non-volatile components are compounds are used here. If we are having volatile components, it is better to use gas chromatography. So if a compound is volatile, that is gas, fragrance, hydrocarbon in gasoline, etc., gas chromatography is better. Then it is used in qualitative and quantitative applications. Just now I have shown you how it can be used in qualitative. So by after getting the chromatogram, we have to compare it with the standard known samples. Then we can easily identify what type of compound is it. So it is used in separation of both the anions and cations also. By using ion exchange mode, you can do that. It is used in forensic chemistry. It is used in separation in lipids. So both polar and non-polar lipids can be separated, as well as the separation of steroids and hormones. So they can also be separated, which are large molecules, by using size exclusion HPLC. And what are the advantages? So advantages at the starting, I told you, it is fast and efficient separation. So you that is fast is nothing. It is nothing but if you compare with column chromatography, because we are applying pressure here, the separation is very fast and it is efficient also. So and it provides continuous monitoring of column effluent. So the column effluent, that is which is coming out, or whatever the mobile phase is entering into the column, everything that can be monitored, because the detector will be connected to a computer which is giving a chromatogram. So in that you can see what are the different components which are present in the sample and which are coming out from the column. So components, separation of components of a very complex mixtures can also be used as sample here, and it is giving rise to an accurate quantitative measurements. So we have seen the food additives. So by just having the data there, which is automatically we'll get from the computer. So the area which is covered under the curve will give rise to the quantity of the sample food additives which is present in the sample. So this is all about HPLC. So hope you have understood, girls. Thank you. Thank you for watching.